Donald Bedford from the Physics Department is going to talk on apparently finite without...
I have to tell you, you forced me to give you a title about 6 months ago, and...
Have you changed your mind?
Well, I haven't changed my mind, but the title, well, you see what you can, see whether you can find anything in the title that matches what I'm actually going to talk about here. Okay. Imagine that you're in deep space. I think it's true to say that everybody here would have to accept the fact that if you were in deep space and there were no stars and there was no matter except you, an observer of some kind, that if the space was completely empty, then any direction you looked in would look the same. Anybody got a problem with that? If it didn't look the same, then you would say, well, it's not empty because there's something about that direction that makes it different from that direction. Empty space is isotropic. Technical word, just means it looks the same in all directions. Has the same properties in all directions. You would also, I think, agree, if you find a problem with agreeing with this, I'd be very interested to know, maybe not right now, but maybe later. You would also agree that every point in that space, that it wouldn't matter where you were in that space. It's an infinite space. It's completely and totally empty. You cannot tell where you are. It doesn't even mean anything to say where you are, because there's nothing where you are with respect to. All points in that space are the same. It is homogeneous. A little harder to take, perhaps, is the notion, because we're so bound up in getting old, and maybe that's part of the reason that many of you are here, and maybe it's part of the reason that we three aging physicists are here, is that time does seem to be different. But I invite you to try and imagine that as far as Mother Nature is concerned, I will use that phrase not meaning anything anthropomorphic about it. As far as nature is concerned, it doesn't matter when you perform an experiment. You could perform it now, you could perform it 5 billion years ago, you can perform it in 5 billion years from now, and you'll get the same result. So time is homogeneous. These are the three statements. Space is isotropic and homogeneous, and time is homogeneous. So you say, okay, so what? Well, it turns out, so lots. So lots. Almost the whole basis of physics relies on those three statements. And what I want to do in the first phase, I suppose, of this little talk is to try and get across to you what I think is the essence of theoretical physics. Because I think theoretical physics is kind of like the closest to truth that we've got. And I'll try and get across this thing. The isotropy of space leads to what is called the conservation of angular momentum. And that simply means that if I took some ball and put it in space, and I spun it, it would spin forever. The Earth has been going around the sun like this, happily, for 4 or 5 billion years, nothing pushing on it to keep it going, it just goes. And it'll go and go for another 5 billion years. That is conservation of angular momentum, which follows directly from this apparently true statement that empty space is the same in all directions. And if we were a little more mathematically oriented, and I'm not going to do any mathematics here, I could prove this to you in 4 lines. I could prove that angular momentum was conserved, meaning it doesn't change from time to time, unless I go in there and do something. If I leave something alone, its angular momentum will be fixed. That homogeneity of space leads to conservation of linear momentum. But if you've got a spaceship hurtling through space, it'll hurtle through space forever. It won't stop. And strangely enough, this homogeneity of time leads to the kind of most famous conservation law of all, which is the conservation of energy. And those three things, it's an amazing thing that this is not widely known. I suspect there are quite a few people in this audience who've never heard of this intimate connection between these three. Not only are these three statements apparently true, this isotropy and the two homogeneity statements, they're so apparently true that they're necessarily true. I cannot imagine them being false. I cannot imagine that an empty space can be non-isotropic. Okay, well, what does that mean? It means that from three necessary truths, and don't forget what the subtitle of this set of lectures is, Search for Truth. Here are three necessary truths. I get some statements about the real world. I get statements that really do make a difference. I mean, when you have this huge Mack truck crashes into the little Beetle Volkswagen, conservation of momentum gives you a whole lot of problems. These are real world things. The conservation of energy is what the whole business of oil exploration and nuclear power and everything is all about. Energy is conserved. You can take it one step further. You can, and I'm going to show this in a little bit of detail, although you'd say, well, what's he doing all this for? Well, I know what I'm doing. Trust me, I know what I'm doing. I'm going to show you that you can actually get from these apparently true statements, you can get statements about the dynamics of the way that the world is. And the dynamics of the world is what physics is about. How do things interact with each other? And what I hope to be able to persuade you, I can't derive for you the stuff. I can't derive for me the stuff. Some of it's far, far too difficult for me, I must say. But I think I know what the ball game is about. It goes like this. Let's take a slightly extended version of this thing with the homogeneity of space and stuff like that. And imagine, and I have to do, some of you might have heard me do this before, but I made it up and I like it, it works. Imagine that you're floating in a box in space. By yourself, nothing to do all day, deep space, nothing to see. You got little bits and pieces of apparatus inside the box. You experiment, you discover the laws of physics. You discover how light propagates and how balls bounce off walls, and you discover everything there is to know about physics, because you got nothing better to do with your time. And one day you see another box come hurtling by, and in the window that you're looking out, you see a face in the window of that box which is hurtling by. So you then speculate about that person's activities, and you come to the conclusion, and again, it's one of these necessary, in my opinion, necessary conclusions, that there's no possible way that the laws of physics that person in that box discovers, there's no possible way they can be different from the laws I discover. That's a hard one. You think about that. It's worth thinking that through and asking yourself the question, well, surely they could get different results or something like that. I don't think so. The situations are completely symmetrical. I mean, they look both looking out the window at each other. There's no directions. Space is isotropic. You then elevate this statement that the laws of physics are the same in all such reference frames, hurtling around at whatever kind of speed you like. You elevate this to the status of a principle. You call it the principle of relativity, and you derive from it the laws of relativistic mechanics, something like this. It actually, I can prove to you an interesting little a piece of the way that relativistic mechanics differs from normal mechanics. Here's a little clock, which is made of a little thing which emits a light signal. And the light signal goes up to the top. It goes flash down at the bottom, and when it gets to the top, it goes click. It's a certain distance. Light takes a certain length of time to go. It's a perfectly viable clock. because as soon as this one goes click, it goes flash down at the bottom again. And so it goes flash, click, flash, click, flash, click, works as a clock. I also have a good to one part in 1 second in 1 million years atomic clock, which is synchronized to this clock. And I also have a biological clock in the form of a hamster. These clocks are all synchronized. Hamsters live for 50 days, and then they die, and then another hamster comes into existence. Perfectly good biological clock. There's a light clock. There's a normal clock. There's an atomic clock. You can have a normal pendulum clock. You can have any clock you like. I go back to the principle of relativity. It said, any experiment I perform in this box must give me the same result as performing it in some other box. Well, let me do an experiment like this. Let me measure the speed of light. There's a pretty absolute kind of thing. Let me measure the speed of light in this box, and let me measure the speed of light in that box. So here we go. Here's one box, here's the other box. You'll see how this connects to that in a minute. Here's a speed of light measuring device. Here's the other box that's hurtling by at half the speed of light with respect to this box. Piece of light comes in the window. Window's closed, sealed. Piece of light goes flitting through this device, and it gives a printer readout of the speed of light 2.99 times 10 to the 8 meters per second. Open window, light carries on. Goes through this light measuring device after the doors are closed here. If this principle of relativity is to be right, then I must get a printout reading exactly the same result for the speed of this same piece of light, which has first been measured by something which is stationary and then measured by something which is moving toward it. That leads to whole lots of consequences. One of those consequences is this. Suppose, here's this light, goes up there, takes a certain length of time. What if I stroll past like this? It goes along here, it goes flash, click. What does that look like to my frame? It looks like this. Flash, click. Because this whole blackboard is moving in that direction relative to me. For those of you who haven't thought about relative motion a lot, think about it. Works. That the F is coming towards me. The F is coming. There it is, flash. There it is, drifting off into the distance there. Well, I can prove to you, I won't do that now because it takes 5 minutes. I could prove to you that this distance and this distance are the same. If the speed of light is going to be the same in both of those frames, which we are led to believe from this principle of relativity must be true, then this clock is going to take longer to click in this frame than it does in this one. The only difference between this clock in this frame and this clock in this frame is the frame. It's the same clock. I just, by moving my body along here, put it into a different reference frame, and by means of that I make it slow down. This whole complex of stuff, if you put it together and you do what Albert Einstein did in 1905, leads in a very straightforward way to the dynamics known as Maxwell's equations. Maxwell didn't use this because it didn't exist at the time of Maxwell's equations. But in fact, if you ask questions about this idea of the invariance of frames, of this symmetry that we're talking about here, of going from one reference frame to another, you get the dynamics of Maxwell's equations, which describes all of electromagnetic radiation. and all of everything to do with electricity and magnetism, if you like. It all comes from this fundamental idea, which I'm trying to persuade you can't be wrong. So what we're getting at here is that some of these, the laws of physics, the ones I'm talking about here, are not like laws of any other kind. They're laws which follow from truths which are somehow self-evident. And I know there's a big problem with using even the word truth, especially with a capital T, and I don't care. Empty space is isotropic is to me a self-evident truth. The fact that it leads to something which is not self-evident, that a spinning ball will spin forever, might be obvious to us now. It certainly wasn't obvious to people 400 or 500 years ago. Okay. You can extend this. Einstein himself extended this. He said, well, look, let's just take this a little step further. He took it a little step further to generalize from these frames, inertial frames which were moving with respect to one another at constant velocity, to frames which were moving with respect to each other any old which way you like. And in the process of that, he developed a thing called general theory of relativity, and discovered, to his amazement perhaps, or perhaps he knew it was going to happen, he discovered the way that gravity actually works. Newton did a pretty good job as an approximation, but the way that gravity actually works, the way that the large-scale structure of the universe is kind of got to be, also stems from what I'm saying is a self-evident truth. There are people who will dispute this with me. I don't care. So we have a happy time, or something like that. We can develop the whole of physics, at least the whole of physics so far mentioned, from self-evident truths. One of these consequences of this thing is that the universe, such a universe, is wholly deterministic. That nothing happens except those things which can happen, and they happen the only way that they can. Every single event is the only event that could have happened under the circumstances of the history of the universe being the way it was. Every single event. Now, it doesn't take too much imagination to see that this is problematic if you want to bring up ideas like free will, because there is no place in such a universe for free will. So people, as this thing developed, and you can find your own history of how the problem of freedom has developed over the years. It's an old problem. It's an old problem. What had to be invented was dualism. That you believe that there could be such a universe, but that there could simultaneously exist in another realm some kind of other thing, spirit, soul, whatever you like. Call it what you will. That existed independently of the material world, and, for example, independent, my soul, or my spirit, or my utu, or my whatever it is, exists independently of this body. And I imagine that there are a lot of people here who believe in the existence of such a soul. And I'm sympathetic. I'm sympathetic to that for the simple reason that without it, we're just a bunch of automatons. We're a bunch of automatons under the physics that I have so far described. And dualism is in fact necessary if you want to be anything other than simply just an epiphenomenon of the functioning of a machine. It just so happens that when you get a machine of a certain complexity going about its business in exactly and the only way it can do nothing else than what it's doing. This machine down here is splabbing away down here, moving its jaws up and down and breathing in and out in exactly the only way it can do. I happen to think that I'm consciously making decisions to say this or say that or talk, having a good time, and all of that is simply the equivalent of the fact that it's similar to my brain being a gray color. It just happens to be a gray color. It's an epiphenomenon of brain cells. They happen to be gray. Another epiphenomenon is that when the brain is functioning in a particular way, I have this sensation of consciousness and a sensation of free will. That was the situation prior to quantum mechanics. Okay, what is the difference between quantum mechanics and classical mechanics? Everything that I've been talking about, the theory of special relativity, general relativity, classical mechanics, classical electrodynamics, are all classical. What's the difference? Well, one illustration of the difference, which immediately is somehow relevant to this discussion that we're having here. I invented this little thing myself. There's a road that runs between Pietermaritzburg and Durban called the N3. Here it goes. It starts in Durban, say, goes up like that, and gets to Pietermaritzburg. There's a road that runs from Ikopo over here to Greytown, suppose, or something. Melmoth. From Greytown to Melmoth, called the R167. Here it goes. Comes along, joins up with the N3, and this is the R167, and this is the R167, and this is the R167. During this stage, there was no point in having two roads, so they just joined the R167 and the N3 together. Now, if you look on a map, you will find that the R167 runs all the way from Greytown to Melmoth. And so during this section here, during that section, the N3 and the R167 are identical. They're not just roughly similar to each other. They're identical in every conceivable respect. There's nothing about them which is different. They're even in the same place. Every single thing about the R167 and the N3 during that section is the same as every single thing about the other road. They are identical to each other. Identical in every conceivable respect. Here are two neutrons. These two neutrons are identical to each other in every conceivable respect. They are so identical that to get the right answer with respect to certain very simple experiments that can be performed, statistical, mechanical things, and so on, to get the right answer, I have to even put them in each other's positions. I have to put this one here and this one here, and I have to put this one here and this one here. That already is a kind of quantum mechanical statement. Don't worry. They are identical. They are as identical as those two roads during that section. I take these two neutrons and I stick them on a plate and I look at them, and this neutron decays in 5 minutes, and this neutron decays in 2 hours. By decays, it means the neutrons do this. They're unstable. They turn themselves into a proton, electron, antineutrino. And they do so typically in about 10 minutes. But some of them do it in 5 minutes, and some of them do it in 2 hours, even though they're identical. Now, what that means is that there's something happening here which is not describable in terms of classical physics. This is the world's shortest proof, I believe, that it is not possible to have a mechanical description of nature. If there was something inside these two neutrons that was slightly different, that made the one decay in 5 minutes and the other one decay in 2 hours, anything you like, anything at all, then they would not be identical. They are identical. Experimentally, they are identical. And so there's something else happening. Well, what else is happening? Well, now it's going to get a little tough. It's going to get a little tough, but let's do it. Some of this you know. Some of this you know something about, I think. In 1935, there was an exchange of letters between Schrödinger and Einstein. Einstein had gone to the States. There was an exchange of letters in which they came up, I think, together. I'm not even sure that Einstein didn't get it first. The thing that has come to be known as Schrödinger's cat. Einstein, maybe magnanimously, maybe because he didn't really get it. It's hard to tell from the letters because they're struggling, these two people, with this idea. And the idea is as follows. I can create an interferometer. I can create an interference pattern using photons. And I can do this by taking a beam splitter, a half-silvered mirror, and another mirror over here, and bringing them together on a photographic plate, and then sending photons in one by one, and I build up an interference pattern. It's just a set of lines. It's a very easy matter to show that you can only get that set of lines by each photon, and here you have to bear with me. I can shine a beam of light and I get the pattern immediately, but I can also get it by sending in one photon at a time. So I send in one photon. Well, what's it do? It either bounces off or it goes through. So you would think. If so, then I would never end up with a pattern, because each photon goes either one way or the other. And the pattern can only be built up because of the differences in distance of these two paths. If each photon went only one way, it wouldn't care about the existence of the other path, and so no pattern would result. The experiment's been done. One photon at a time, the pattern results. So quantum mechanics, although not invented for this purpose, in fact, the quantum mechanical expression of this thing is, and here you have to just take my word for it, the photon goes this way and not this way, and it goes this way and not that way. And that "and" is a quantum mechanical plus sign between two wave functions, and it has no classical counterpart. So I write something like the state of that photon when it's going here is some sort of a superposition of going one way and not the other, and the other way and not the one. If we had more time, we could deal with this. This is a little course in quantum mechanics over here. We don't have time for that. I just want to accept for the moment, dispute it like crazy later. The formalism of quantum mechanics allows you to predict the formation of this thing. So you then say, okay, we've got this funny little plus sign here. This plus sign exists. Schrödinger and Einstein together realized that there was a problem with this. Because if you do this, and you take and you put, this is the Schrödinger cat story, you dangle a piece of potassium, my chemistry is not great, but potassium cyanide here, and you put some hydrochloric acid in a bowl, and you arrange it so that if a photon comes along, it will snip this little string, and the cyanide will fall into here, and this cat that's sitting in the box will be killed. If, on the other hand, the photon is reflected, then the cat is not killed. This is path 1, and this is path 2, or this is psi 1, and this is psi 2. But we have a situation which we have shown is the sum, this quantum mechanical sum of these two things. The net upshot of this is, and that's the paradox, is that the cat goes into a superposition of states of being simultaneously alive and dead. And that paradox has stood the test of time. There's no resolution to this paradox because, and now we're getting close to what I want to really get at here. This thing here, that plus sign, there's no mechanism within the quantum mechanical formalism which simply just evolves the state with what's called a unitary operator. A unitary linear operator evolves that state over time, no matter how complicated the system gets. The plus sign stays there. This is what Einstein and Schrödinger, with their rather good handle on the subject, were able to realize is that it didn't matter if it got as complicated as the cat, the plus sign stayed. And if the plus sign stayed, so would your brain state when you looked in the box. That somehow some part of your brain should go into the one state of seeing the dead cat, and the other part of your brain should go into the other state of seeing the live cat. And so you should simultaneously be in this superposition of states. You're not. That is the problem of measurement in quantum mechanics. Quantum mechanics predicts that such a measurement should not be able to take place. Such measurements take place. They take place all the time. Every time you look at that light bulb, you're seeing billions of photons, which were going in all different directions, but now happen to hit you in the eye. You force that situation. The dualistic response to this, of course, was very immediate and put up by von Neumann and by Wigner. Big noises. These are non-trivial people in the 20th century physics. They said, okay, it's true that your retina, when you look in the box, your retina goes into this superposition of quantum states that we don't understand. The plus sign sees the dead cat, sees the alive cat. The optic nerve takes the signals back from the retina and into the brain, and the brain processes like crazy on these both things, because the plus sign remains. And then the spirit looks at the brain and the wave packet collapses. The brain's the conscious human awareness takes the plus sign away. And it's the only thing in the universe that can do it. Now this was very, very interesting. Dualism, which was necessary within a classical framework to get away from determinism, now becomes necessary within a quantum mechanical framework to make the thing work at all. That the quantum mechanics becomes a silly thing. So silly, let me tell you how silly the solutions to this problem have been. There have been many solutions to this problem. That Wigner-type consciousness collapse is only one. There's one that says it doesn't go away. And indeed, your retina and your brain go into this superposition of states, and so does your mind. And the universe splits into two pieces, and in one universe you see a dead cat, in the other universe you see a live cat, and forever thereafter there are these two universes. And this happens for every single quantum event that happens in the universe. So we have a multiplicity of universes, which, as far as I can make out, is not only infinite, but is continuously infinite. I mean, you can't even count the number of universes there would have to be for that to be true. So that one I give a miss to. This consciousness thing. Now you say, well, okay. One of the things you can say is, well, can we test it? And I'm not going to go into the details of that. The answer is yes. And indeed, an experiment which was performed at this very university some 25 years ago by one Derek Wang and Donald Bedford showed that Wigner's suggestion that consciousness could be the mechanism whereby this quantum plus sign was taken out of the equation was false. Then what? Well, you could just say, well, let's just go back to the epiphenomenon story. You got the brain state, and I have this impression of being conscious. I have an impression of control, that I can make decisions. All of that is absolutely false. My brain is going through, it's no longer a fully deterministic system because of the kind of indeterminism associated with quantum mechanics. But it is kind of irrelevant. So it's a little bit indeterministic. It's got a random side to it. It doesn't help me, doesn't give me any control whatsoever. So what about the free will? Am I back to this thing? And I think the answer to that, and here it's treading on slightly tentative territory, I think the answer is no. And I think the reason for that is something like this. There are a number of analyses you can perform. A friend of mine who lives in California, at Berkeley, Henry Stapp, who is one of the fairly big deals in this field. He refers to Bell's inequality, or Bell's theorem, as the most significant discovery in the history of science. Now that's a fairly astonishing thing for anybody to claim about anything when you're talking about discoveries of the kind that physics has made over the last 400 or 500 years. But be that as it may, what does Bell's inequality do? I can't go through it. It's a little technical. What it says is this, is that you can have systems which are in states of the following kind. I promise not to do any mathematics, but it's not much more difficult than this. States of the following kind. Let me write it like this. You like these kind of symbols. I'm sure you like these kind of symbols. Dirac invented these things. This is called a ket, and this is called a bra, because together they form a bra-ket, a bracket. Now that's apparently the reason. This first thing here, this is a two-particle state, and it refers to the arrow refers to the spin of one or other of the particles. This says particle 1 is in spin up and particle 2 is in spin down. And this says the reverse. Particle 1 is in spin down, particle 2 is in spin up. So you can produce such a state. It's called a non-separable state, and these days they're giving it another name. I'll stick to non-separable. It's a non-separable state because I can't write it as a state for the one particle times a state for the other. They're linked. They're linked with this quantum plus sign. Now, I can take these two particles, and these are the experiments which have been done since Bell published this thing in 1965 or something. Experiments were done not for a few years, but then in the 70s and into the 80s. And there's still experiments being done. I've just remembered the word, entangled. I don't like it very much, but that's the 21st century term for such a state, is entangled. Okay. I can take an experiment which I take one particle out this way and one particle out the other way, and I can take them as far away from each other as I like. And they remain in this state. Now, I have to tell you that if I make a measurement on particle 1, Suppose this is particle 1 going over here, and this is particle 2 going over there. If I make a measurement of particle 1, it forces, and I find this result, say, spin up, it forces this result on particle 2 because of angular momentum conservation, where we started, in fact. That the total spin must add to 0, so they have to be opposite. So if I get this for particle 1, I have to get that for particle 2. And this whole thing goes away. But that's exactly what I want in this solution to the measurement problem. I want the quantum plus sign to go away. Well, I just make a measurement and away it goes. Doesn't solve the measurement problem. But it does do something else. It introduces a whole new feature. This thing can be as far away, particle 1 can be as far away from particle 2 as you like. It can be 1,500 light years away. Making a measurement there immediately forces a shift in the condition of particle 2. We didn't talk much about relativity. Relativity says you cannot send a signal faster than the speed of light. It follows very rapidly from that stuff that I was doing there. This is true. You can't do it. You can't send information faster than the speed of light. Somehow, this information that particle 1 has been measured, and indeed the spin is up, this information somehow gets to there, to particle 2, over arbitrarily long distance, arbitrarily fast. When this first was realized, people said there's something terribly wrong. It can't be true. Because that's a breach of special relativity, and special relativity, I tried to persuade you at the beginning, was true. Well, what does happen? Well, it turns out there's no information sent. Because all that, think of what you have to do to send information. I make a decision, like I am going to start smoking. And I want to communicate to that to somebody 1,500 light years away. And I want to use this system to do it. I can't. Because there's no way I can link my decision to starting smoking to the result that I get either up or down when I measure spin 1. I mean, the spin of particle 1. There's no way I can link that. I have to actually send something. But these things don't have to send anything. So why do I have to send anything? These things are happy to participate in this non-local interaction, this non-local quantum mechanical intimate interaction with each other over arbitrarily long distances, and no one complains. No one says there's anything special about that. There's no breach of special relativity. So I say, well, look, I'm still struggling with this problem that I have about my place in this whole scheme of things. Here I've got all these nice little particles and everything, and I believe that I'm made of nothing more than them. They all participate in this stuff willy-nilly, helter-skelter, all day long. So is it possible that people have been unable to shake off this dualistic thing, that somehow they wanted to separate this spirit away from this physical thing here for reasons for ancient reasons, for reasons that were perhaps germane in the 19th century, before quantum mechanics. And what they haven't been able to do is to bring themselves into a quantum way of thinking about this thing, and realize that they can be participants, not simply passive observers, in quantum mechanical phenomena in a way that they couldn't be in a classical situation. And I think, unless something pretty funny happens to me over the next 20 years, I'm simply going to gradually settle into understanding what that means. That I'm not distinct from my body. This has the immediate consequence that when the body goes, so do I. But it also does not remove from me this idea of will, that I can feel responsible for my actions because I'm an active quantum participant with these little things that actually make me up anyway, and I don't have to do it by somehow coming from outside the system and interfering, that I'm doing it from within. And I have to be able to do it from within, and quantum mechanics allows me to do it from within through, granted, a very messy and very complicated and very difficult procedure, allows me to participate from within without losing all control, I don't know, all sense of, I like responsibility. I'm a participant observer in the goings-on of the world. I'm participating. I don't believe that I'm simply being a passive entity. You can then say to me, well, is this then your soul? Well, I'm not talking about soul. I'm talking about quantum mechanics. Quantum mechanics is a very different thing from anything that I've ever encountered before in my life. And I certainly will never encounter anything as peculiar. It is so close to, it is so similar in some sense to the problem of consciousness that it would be hard to imagine that they weren't intimately linked together. It's so close to the problem of somehow of spirit and the non-mechanical nature. Remember, I said this little neutron thing. Quantum mechanics does not allow for a mechanical description of nature. These two things, whatever is going on with these two particles, it's not mechanical. There's no signals, there's no waves, there's no fields between them, there's nothing. And yet they are intimately involved in each other's activities. What happens to one affects the other. And that's kind of what being alive is like, I think, isn't it? I mean, you interact for a while, you participate in things, you exercise judgment and make decisions and all sorts of things, and then you die. Thank you. Okay. I guess the last line tells you the essentially finite or apparently finite part of the story. Okay, I don't know what time it is.
It's not time to put my hand here.
Okay, questions would be most welcome, or suggestions, or instructions, or anything. John?
If I may just ask at this stage, just going right back to the beginning of your remark on the homogeneity of time and the complete reproducibility of experiments in the course of time, like billions of years ago or billions of years in the future, brought to mind this, to many people, was a very strange idea of Dirac's, that the fundamental constants could be time variable, which would in fact lead to very different results over very long periods of time. Would you say exclude this idea is on this ground?
I think that the question has to do with the possible variation of the fundamental constants, like the speed of light or Planck's constant and so on, that these things, the gravitational constant, that these things could change with time. This was a suggestion of Dirac and other people, I guess, over the years. I certainly wouldn't rule this out, but I also wouldn't rule out energy not being conserved either. Can I just make a remark with respect to a question that was asked last week, actually, that I think maybe this is important. Since we're putting our own points of view here, I can put my own point of view. The question had to do with the origins of the universe, the Big Bang. I will tell you why I don't have a problem with the Big Bang in terms of any conservation laws or anything to do with it, really, is that my understanding of the Big Bang is that there's no before the Big Bang. The Big Bang is not an event, because there's not any time passing for events need nothing to be happening for a while, and then the event occurs. There's no time. So there's no possibility of an event. So the beginning is not the end of nothing happening and then the beginning of something. You can call it a beginning if you want, but there's no before. It's very hard to find language to talk about a situation like that, I can tell you. There's no before this event. And there are also no laws of physics. There are no laws because there's nothing. There's nothing at all. I mean, there's no space, there's no time, there's no matter, there's no energy, there's absolutely nothing. Not sort of an empty space or anything, there's nothing at all. And therefore, there's nothing to prevent anything from happening. And so the Big Bang's as good as anything else. Maybe the laws of physics are the way they are. I think quite a few people sort of tend towards this. I tend towards this myself for reasons that I was trying to get at with respect to these conservation laws and the dynamics. Is that I have a sneaking suspicion they couldn't be any other way. It's not that they are the way they are through any anthropic principle or because this is the best of all possible universes and things had to be this way in order that we come into existence or anything. I think they're the way they are because they couldn't be any other way. Whether we as physicists or anybody else as anything will ever be able to show that this is so. I have a sneaking suspicion Stephen Hawking thought he was getting onto something, but I have to tell you he lost me somewhere along the way in that book of his. I don't think anyway, it's quite possible, in principle, I can imagine that at some future date it is possible to show why the laws of physics are the way they are and have to be the way they are. And there isn't another possible universe. There isn't. This is it. But people disagree.
I've heard, I'm not sure if I can express my question, but you have positive particles and negative particles, which collapse into nothing. So why couldn't the Big Bang be where presumably you need some matter and so on? And you can borrow from a bank and make matter.
But you don't. When you get a particle and an antiparticle collapsing into each other, they don't collapse into nothing. They collapse into a whole bunch of energy. I mean, so it's not kind of like the opposite of the Big Bang. The Big Bang really is nothing, followed by something. So there's no borrowing possible. I know that people have talked about quantum fluctuations. Well, I know something about quantum fluctuations, and I happen to know that in order to have quantum fluctuations, you A, need space, and B, you need quantum. Something in there, you need some kind of quantum mechanics, and you haven't got either. So the idea of a quantum fluctuation in nothing is a little bit ridiculous to me. I'd rather just have nothing and then something, because there's no reason not to. Peter, you had a...
I just want to go back to what you just said about the laws, the way it is being necessary, the laws being necessary. So it's not something that's derived logically or mathematically or anything. It's a metaphysical assumption. It's an accident. You start with that position. And I wondered what makes you, what inclines you to that position. Know why you have that feeling that it must be that simple.
Well,
room for contingency.
I like the idea. I suppose it's one of the reasons I went into physics. I like the idea that there were some fundamental truths. I was raised as an atheist, or well, I'm not even an atheist. I mean, I was raised without any sort of notions of the existence of God, except what I knew friends of mine, then things went to church and Sunday school and things like that. But I was raised as an atheist. So maybe it was because maybe this is a lacking in me, that I really was kind of interested in finding out whether there were any absolute truths around the place. And if you ask yourself the question, well, what subject shall I take up, which is going to give me the best possibility of finding out some absolute truths, if there are any, then it's certainly not going to be commerce, or probably not philosophy, and I would think not even mathematics, because you can do anything in mathematics. You can make up any system you like. In physics, you can't. You can't. You're constrained by physical reality. And so I mean, at some level, maybe look, I certainly wasn't consciously doing this when I went to university and did physics. I was interested in it and I was good at it and da-da-da. So that's why I did it. But Peter, look, I mean, you can. I mean, it is an astonishing thing to me that you can from something as necessarily true as the invariance of the laws of physics under a transformation from one inertial frame to another, which is special relativity, that there comes Maxwell's equations as the simplest set of equations which are invariant under that transformation. And Maxwell's equations tell you everything practically there is to know about light. And I mean, that's an astonishing thing to me. That, in other words, it would appear to be the case that you couldn't have anything else other than Maxwell's equations. And that almost means that you almost have to have electric charges, and you almost have to have the interaction between these electric charges being completely determined. I mean, it starts to get a little on the technical side, but that's the flavor. That's the sense that I'm trying to get across. It's certainly not there. I mean, there's a whole lot of physics which is just made up, and people do things. And nuclear physicists were particularly good at just you had what were called empirical or semi-empirical formulas, which would have about 25 different parameters, and you could fit any curve in the universe with these by varying these parameters around and stuff like that. That's not what I'm talking about. I'm talking about the fundamental laws of physics, supposing that there are some. Yep.
Just a physics question. I think the old thinking was after the Big Bang that everything will collapse again, but now there is a new theory that there is an anti-gravity, and how would you explain the force of outside anti-gravity which is pulling actually everything?
I have no idea. I know what you're talking about, and when I first heard this, I thought this is really going to hit the headlines if this is true. And I suppose, as far as a physics discovery, if that's what it is true, I suppose it has hit the headlines as much as these things do, that don't have immediate consequences like hydrogen bombs or something. Yeah, it's astonishing thing. I have no idea. I mean, you've got a whole new. It might. I haven't really heard any coherent discussion about this, I must say. It might mean that some ideas like this isotropy, homogeneity of space, are going to have to go by the board. Fine, such is life. But we're not talking here about an empty space. We're talking about a space that's actually got lots and lots of matter in it. So that could be different from an empty space. You could still have an empty space which was homogeneous and isotropic, and it becomes a little bit problematic. I don't know what to make of that stuff. I don't know what to make of it. If you look at the actual data from which they're getting this, I don't know how hard that data is, how reliable. I'm not in a position to judge, so here I have to now accept the opinions of astronomers and people who know about these things. And look, I think the situation is as yet fluid. I don't know, Sarah. I don't know if you followed this any further.
No, I don't think
This is a couple of years ago. There was an announcement that the universe is not only expanding, it's accelerating in its expansion. That instead of expanding and slowing down because of gravity, everything is going up the gravitational hill, and so it should be slowing down. But these people, by looking at supernovae, I think, they've got out to distances like about 10 billion light years, which is as close to the beginning as you need to go. And they've got sort of 50 or 100 supernova events, and these particular kinds of supernova events are very similar in output for reasons that I don't understand. And so by looking at the brightness and by looking at the redshift, you can make statements about the situation now, currently going on, that you couldn't make before 2 years ago. And the statement that you can make that these guys are suggesting is true is that rather than slowing down, this thing is actually accelerating, speeding up. That the thing is flying apart with greater and greater speed. Okay. Why not? But exactly how that force would work, got no idea. It's new. It's new. It's not anything like... it may be related, and some people have suggested it's related to... You can write it into the Einstein field equations in terms of maybe even Einstein's cosmological constant, which he wanted to put in to show why the universe was not expanding. Because at the time he came up with the equations, it was not known that the universe was expanding. He wanted a static universe, so he had to add this term in. Now maybe you have to add the term in to explain why the thing is expanding ever faster, or something. I mean, can I make it clear what I think? I mean, I think I probably have. Well, I've tried to make it clear. I am a collection of atoms and molecules, but I'm not a determined by outside forces. I participate in this thing in a quantum mechanical way. I have an understanding of that which I haven't really, in any sense, been able to get across to you because it's not even clear to me, and to understand quantum mechanics is in itself quite difficult to actually get the message. To do quantum mechanics is pretty easy. You write down equations and solve them. But I actually get an idea of what this means, what this implies about the relationship between this collection of atoms and molecules, amongst those atoms and molecules, and between them and atoms and molecules, and whatever you like in the rest of it, is different from the way we were all brought up to look at billiard balls colliding and things like that. It's a different story.
You talk about empty space, which sustains objects.
How can I talk about empty space?
Which sustaining objects.
Sustaining them. What do you mean by sustaining?
Doing a diagram of if they take off and get going to
Okay.
indefinitely.
Move indefinitely.
But it's sustained in apparently speak of empty. Look, I don't know.
No. This is a wonderful question. If I understand the question correctly, you're saying how can empty space sustain anything since it's
Using the word empty.
yes,
It seems to me it's not empty.
because it sustains.
Something. Hawkins says either. I don't know this word.
It's very interesting that you make that remark, because people did believe that in order, I mean, how does a little, here's my billiard ball way out in deep space, and I throw it like this. What tells it to move at constant velocity? Why doesn't it just, how does it know constant velocity from non-constant velocity? Surely there's got to be some standards around for it to know, yes, now I'm traveling at constant velocity and so I'm obeying the rules. If that's the content of your question, then that's an extremely good question. And people did suggest there had to be something about empty space that can act without being acted upon. Those words are Albert Einstein's, in fact. I don't know. It's a very subtle thing. The shift from standards of non-acceleration, standards of rest. I mean, if we're living in a universe which is finite, probably finite but unbounded.
Unknown.
Well, unbounded, like the surface of a sphere. It doesn't have any edges, but the surface area is finite. I mean, it's this big. But you can't find where it ends. You can crawl around on there forever and never come to the end. Well, this three-dimensional universe we're living in is supposed to be of a similar nature, one dimension up. So you can crawl around on it forever and go in any direction you like forever, and you don't come to any edges. And so there's no point that's special. Every point is just the same as any other old point. Where did the Big Bang happen? It happened everywhere. Because that's all there was, that's all the where there was at the time of the Big Bang was that point. And that where expanded out, and then here we are. Okay.